Angles in the unit circle. So a couple of terms here that you need to know. Standard position is the first one. When the vertex is at the origin, that is 0, 0 on a coordinate plane. And one ray is on the positive x-axis. The ray on the x-axis is the initial side. Initial meaning where it starts. The other ray is the terminal side, where it ends. All right? So in standard position on a coordinate plane, your vertex is located at the origin. You have the initial side that goes out the x-axis, and then you have the terminal side somewhere else on your coordinate plane. All right? Terms you need to know. So then what you start doing is you start using what you know about the coordinate plane to look at angle measurement. So look at example 1 here. Find the measure of the angle at the right. Well, let's see. How do we find the angle measure? And this is without using like a protractor or something like that. Okay? So I know the angle measure of this guy right here. What is this angle? That blue one I just drew. And why do I know that's 180? Each one's 90, and it's a line, right? It's a line. And so if I know that angle, then how can I calculate the whole angle? There we go. So I have the 180 for the straight angle. That is not very easy to see. All right, I have the 180 for the straight angle plus the 20, and I have a 200-degree angle. Simple enough. Standard position. It started here, and it went around to a terminal side here. Okay? So go ahead and answer that just thinking problem down there. All right, so let's talk about this. One full rotation is 360 degrees. Obviously, one full rotation is a circle. How many degrees are in 1/4 of a rotation? 90. What about half a rotation? 3/4. There we go. All right. 90, 180, and 270. All right. Let's look at the next thing. The measurement angle is positive when it goes counterclockwise. It is negative when it goes clockwise. All right? So in standard position, if you start here, which is standard position, and you go counterclockwise, that is a positive movement. For those of you that have done vectors in physics, this is also what they use for standard position. If it says standard, it's counterclockwise for positive and clockwise for negative. So negative here then starts at the x and then goes down clockwise, right? So clockwise for negative, counterclockwise for positive. So let's look at sketching angles. Sketch an angle in standard position. Okay, so here's the deal. When you're sketching, it doesn't mean that you need to get a measuring tool out and do something. You are simply just sketching it. So 36 degrees, you want to figure out what quadrant of the coordinate plane it would be in. So if I know specifics, this is 0 degrees. What is this straight up? 90 degrees. We just said to the left is, and down at the very bottom is. So if I'm sketching it and I have a 36-degree angle, I know it's going to be in which quadrant? My quadrant 1. And it's going to be less than halfway through it. What would halfway through it be? 45. So if I were just sketching this guy, I would probably go somewhere about here, 36 degrees. All right? Easy enough. 315. Well, I have 0, 90, 180, and 270. Which quadrant is 315 going to be in? Yeah, it's going to be in my 4th quadrant. And this one is actually a specific one, right? If this is 270, how far away from 270 is 315? 45. So this guy should be right directly in the middle there. All right? And you need to know that it goes like that, right? Whereas this one just went here. Okay? Then let's look at the last one. We have negative 150. So if I'm negative, and this is 0, in the negative movement, what is this guy down here? Negative. Negative 90, negative 180, negative 270, right? And so if I'm at negative 150, which quadrant am I in? 3rd quadrant, right? I am how far away from 180? 30 degrees. So I'm about right here. Well, that's not quite 30. About right here, okay? That would be approximately negative 150. Everybody see how we're sketching these? All right, so go ahead and try A, B, and C. Sketch those. Let's look at these. 85 degrees. What quadrant should that have been in? First quadrant, right? This is less than 90. Negative 320. Where was he?
First one.
Yeah, he went all the way to the first. All the way to the first quadrant. Because he went negative. All right, what about 180? That one's right. Yeah, it's right on the line, right? Positive 180. So that's what those should look like. All right. Let's look at coterminal angles. Two angles in standard position are coterminal if they have the same terminal side. That makes sense, right? So they give the example, positive 130 and negative 225. They have exactly the same starting point and ending point. And what you'll find as we get into trigonometry, they have the same trig values as well. They are, in essence, the same angle, okay? What you'll also notice is if I take 135, what happens when I take 135 and I subtract 360? Go ahead and do that and tell me what you get.
Negative 225. You're so smart.
Negative 225. They're exactly one full circle away from each other. So if I gave you the angle 135 and I said find a coterminal angle, you could subtract 360. You would get negative 225. You could also add 360. That would also be a coterminal angle. Angles are not always less than 360 degrees. They are any measurement because your trig functions and all of these are periodic. They are cycles, and they cycle because they're based on a circle. And so you could add 360 or subtract 360 to get a coterminal angle. Talk about what the unit circle is. Circles have a radius length. All circles have a radius length, right? We have, over the years, calculated circumference and area based on the radius length, all right? In a unit circle, the unit circle has a radius length of 1 unit, hence the term unit circle. The radius is always 1 in a unit circle, all right? So the unit circle has a radius of 1 unit, and its center is at the origin of the coordinate plane. Points on the unit circle are related to periodic functions. You can use the symbol theta. So this is a symbol you will see. Theta, it is just a Greek letter, for the measure of an angle in standard position. If you study vectors in physics, they will often use theta, all right? Because that is standard position. So let's look at what cosine and sine mean. We are familiar with sine and cosine. How are we familiar with sine and cosine? What have we done in the past? Geometry. And the shortcut for it is called Sohcahtoa, all right? So suppose an angle is in standard position and has a measure of theta. That's just the angle measure. The cosine of theta is the x-coordinate of the point at which the terminal side of the angle intersects the unit circle. So let's talk about why this happens, all right? So I'm going to take this guy and I want to talk about why the cosine and the sine are what they are on the unit circle before we start moving to it. It says the cosine of theta is the x-coordinate. The sine of theta is the y-coordinate. That works. Why would it be the x value? Well, let's say I take this guy right here and I connect and go straight down here. Let's make him a little bit thicker. All right, connect that down there. All right, it's a triangle. It's a specific type of triangle. What specific type of triangle? It is a 30-60, but it's a right triangle, okay? And so I am talking about this angle right here, okay? What is the radius of my unit circle? It is always what? So my radius length here is 1. Radius happens to be what of this right triangle? Which side?
Oh, the hypotenuse.
The hypotenuse, right?
Hypotenuse over adjacent.
Well, that's like another trig function, but we'll start with sine. All right, so let's start with sine. Sine is Sohcahtoa. So sine is what? Opposite over hypotenuse. Shh. All right. Now, let's talk about this point right here on my unit circle, all right? This point is xy, correct? That's how we always do points. What is the height of that point?
1/2.
Just in variables. What's the height of that point?
Oh,
The height is x?
Y.
Y. Yeah, so my height is y. That's too thick. My height is y, correct? What is my length here then?
Your X.
X. Yes?
but equals 1.
Okay? It doesn't go all the way to the edge. So if I start from here to here, I should get my x value, right? And if I start from this point to this point, I should get my y value. Everybody agree with that? So I basically have this triangle here with a y value there and an x value there. And my hypotenuse, we said, was 1 because it's the radius of the circle, correct? So if this is theta, correct? We know that's theta. How then would I find my cosine of theta and my sine of theta?
Divide your cosine by your
So let's talk about, we just said sine was opposite over hypotenuse. What is the opposite then of this angle theta? What's opposite? Which side is my opposite side up here?
X, Y.
Opposite is,
One.
adjacent is,
X.
and hypotenuse is 1. All right? We good so far? So my cosine then, what's my cosine going to be? Adjacent over hypotenuse. So what is it? It is x over
Y.
1, which is x. Yes?
Yes, yes, yes.
All right, sine is opposite over hypotenuse. What is my opposite?
Y1.
Y over 1, which is
1.
y. All right, everybody see that?
Yes, ma'am.
Now let's look at what they just told us. Because of this, that works because of Sohcahtoa. All right? So we introduce the unit circle and we start saying, oh, the cosine is the x, the sine is the y. But the reason that works is because of right angle trigonometry. It's just opposite over hypotenuse and adjacent over hypotenuse. It's just that your hypotenuse is 1 in a unit circle. So you only have to worry about opposite. Well, opposite is my height. That's my y value. Adjacent is my width, which is my x value. So you don't even have to worry about over hypotenuse when you get to unit circle because the hypotenuse is always 1. You just have to worry about your x coordinate, that is your cosine, and your y coordinate, that is your sine, okay? Because it's just x over 1 or y over 1. So then how do we relate this to finding things like sine and cosine? So let's look at example 4. Find the cosine and sine of 60 degrees. And now they have given us our special right triangles, all right? So the special right triangles is just here to help you learn. You're not going to end up using it. You're just going to end up memorizing some special cases, okay? So let's recall our special right triangles before we get started. For a 30, 60, 90 special right triangle, you have a short side, right? The hypotenuse is always double the short side. And the long side is always the short side times the square root of 3. Okay? So far, so good?
Wait, the river.
At special right triangle, 45, 45, 90. All right? For a 45, 45, 90, we have the side lengths are the same. And the hypotenuse is side square root of 2. All right? So they want a 60-degree angle. We are going to sketch this guy. So a 60-degree angle is going to be in which quadrant? First quadrant, right? So he's going to be about right here, right? Where he ends is right here on my coordinate plane, correct? All right, if I were to make this into a right triangle, this is 60. We just determined that was 60, okay? So what type of triangle is this? 30, 60, 90, all right? So I know that this is my short side, correct? So then this side should be times the square root of 3, correct? And this should be 2 times s. Everybody see that? So let's figure out my cosine and sine. All right. So let's talk about cosine. Cosine is adjacent over hypotenuse. Correct? What is the adjacent? So let's label this guy. Which side is the adjacent side? S squared of 3 or 2s? S. What's opposite of my 60? S squared of 3, right?
How do you know which one's adjacent?
And what's my hypotenuse?
20, or that's at
2s, okay? How do I know which one's adjacent? All right, it's the one, so you have two sides that make up your angle, right? If I'm talking about the 60, you're gonna have this side and that side. This side is already pre-named, hypotenuse. The other side is the adjacent. If I stand in my 60 degrees and walk across, I run into my opposite.
So it's
Okay.
the one attached.
So in this case, tell me, in terms of the variables that I have, what is my adjacent side over my hypotenuse?
S over 2s.
S over 2s. So I have my adjacent side over my hypotenuse. Can I simplify that?
1/2. You can't even take out that.
1/2, right? Everybody see that I can simplify that? Let's look at sine. Sine is opposite over hypotenuse, correct?
Yeah.
What is my opposite side? S squared of 3, and my hypotenuse is 2 times s. I can simplify that. How does that simplify?
They got S square root of 3 over 2.
Square root of 3 over 2. That is my cosine and my sine of a 60-degree angle. Let's talk about what cosine and sine means. We talked about it a little bit when we did Sohcahtoa, all right? Sohcahtoa told us it's a relationship between two sides of the triangle that's made up by that angle, okay? So I want you to understand that whether I have a 60-degree angle that is the size of this thing on the screen here, or whether I have a 60-degree angle that NASA is using to calculate where a satellite is located, the ratio between the opposite and the hypotenuse will always be square root of 3 over 2, and the ratio between the adjacent and the hypotenuse will always be 1/2. No matter whether I'm talking about a triangle that is small enough to write on a piece of paper or a triangle that takes up millions of miles in space, the ratio between those sides will always, always, always be these fractions for any 60-degree angle, okay? That will always be the ratio. That's all that sine, cosine, and tangent are telling you. They're telling you a ratio between two sides of a triangle that is made up by that angle and a 90-degree angle, okay? So that's what sine, cosine, and tangent are telling you. And so you can use, what we start doing here is we start figuring out specific things on the unit circle that are repetitive, and you start seeing it. And so we're just starting to build that a little bit with this. All right, so what I want you to do is A, B, and C. They want you to draw the angles, sketch them, and then find the cosine and sine. For right now, I want you to do A and B, and then we're going to talk about C. So for this first one, this is what it should have looked like. Your 45 should have been halfway in your first quadrant. Side, 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 square root of 2. All right? So that means your sine of a 45-degree angle is going to be opposite, which is side, over hypotenuse, side square root of 2. When you reduce that, you get 1 over the square root of 2. You don't leave it that way, though. What do you do?
Oh, you gotta get this.
Got to rationalize it. So you got to multiply the top and bottom by the square root of 2 here.
Square root of 2 over 2.
So you end up with the square root of 2 over 2. That is your sine of a 45-degree angle. Square root of 2 over 2. All right, cosine.
I forgot about that.
Cosine of 45 is actually the exact same thing, right? Because your sides are the same length. And you get the exact same thing, and you rationalize it exactly the same way. And you get square root of 2 over 2 for both the sine and the cosine. All right? Let's look at your 30-degree angle. 30-degree angle is going to be somewhere about right here. And it ends on the unit circle right there. All right. This is my 30. This is my short side, correct? Short side's always opposite. All right, so my short side's always opposite my 30-degree angle. So my short side is my height here. This one then would be side square root of 3, and this would be 2s. Okay, So if I do my sine of a 30-degree angle, then I'm going to say opposite s over 2s, which is 1/2, right? If I do my cosine of a 30-degree angle, I'm going to say s square root of 3 over 2s, which is going to reduce to square root of 3 over 2. And that is my sine and cosine of a 30-degree angle. All right. The last one we're going to look at is 120. So 120 is 30 degrees past the 90 mark, right? 30 degrees past the 90 marks. We're going to put that one about right there. If I draw this right triangle then, I'm actually going to draw straight down. Okay? Now, that means I want this angle measure. How far away is that angle measure from 180? If I'm at 120? 60. So it is 60. So again, I have a 30, 60, 90. My short side is here. My long side is here. And this is, again, my hypotenuse. And if I do the sine of a 60-degree angle, we actually already did this one, didn't we? Side square root of 3 over 2 times the side, square root of 3 over 2. And if I do the cosine, then I get just my side over my 2 side, which is 1/2. Now, you will notice that a 120 and a 60 had the same measurement. But what we have to consider is positives and negatives. All of a sudden, I no longer have exactly like a 60-degree angle, because the 60-degree angle is in which quadrant? First. Which quadrant was a 120 in? Second. So what do I know about the value of my x's and y's? In my first quadrant, my x's and y's are both what? Positive or negative? Positive, right? But over here, what happens?
Your x is negative.
My x is negative and my y is positive, all right? So that means this was a negative s value, correct? When we think about a 30, 60, 90, we think, oh, just distance. It's always positive. But when you put it on a unit circle, positives and negatives all of a sudden matter, okay? So that means this coordinate represented by my x and y, the cosine and the sine value will follow my positive and negative of my x's and y's, meaning my cosine in this quadrant will be negative, my sine in this quadrant will be positive. So my cosine for this guy is negative 1/2, and my sine is positive square root of 3 over 2. So even though the numeric value or the absolute value of them was the same as a 60 degree, which is how it will always be, where it falls in your coordinate plane matters for positives and negatives, okay? So that means sine is positive square root of 3, cosine is negative 1/2 there.